So I mentioned in passing the term NDVI. So let's have a look at what that actually is. This relies heavily on this jump up here, this difference between the visible light down here and the near infrared here. Vegetation reflecting strongly in the near infrared and relatively weakly in the red or the green, or indeed the blue. So we can perhaps use this effect. If we can strengthen that in some way, if we can identify cells or pixels in our image where we can see this relationship strongly, then that's indicative of it being vegetation rather than, say, a very warm road surface. So let's see what we can do with this, and why does it work? Well, we can see that the absorption of light, so the reason the plants are green is because they absorb a lot of light in the blue and the red because they have chemical compounds within them that are capable of grabbing hold of the light of that frequency and then taking that energy and converting it into sugars in combination with water. It's photosynthesis. The green light tends not to be absorbed. It tends to pass through or be reflected. So if we look at that combination and say and decide and try to work out some measure of how big is this difference. So if we were to, for example, just look at the absolute difference and say how much bigger is this than this in terms of just subtracting one from the other. The problem with doing that is that in varying light conditions, we will get different measurements. The same plant even would look different given different illumination. So if it's in shade, then there's not much light to be reflected. And so the total signal will be smaller, weaker. So measuring the absolute difference in signal strength actually isn't that useful for us. We want the relative change. And in order to get that relative change, we will normalize the strength of the light. Normalizing it by adding the strength of the near infrared and the strength of the red together. That's our normalizing number down here. And then we will normalize that difference. This is we are interested in this difference, so we will calculate how big a jump is there and then normalize that number so that even if it's a weakly reflecting signal, we're still getting the same normalized difference because we're saying that the total amount of light available to create this jump was much less or much more. So we're normalizing the size of that. So if you like the illustration, so depending on how big that is, we normalize it to create a standardized value. This is how reflective it is due to vegetation. So our NDVI takes care of this variation in the strength of the illumination and just looks for how strong is this relationship between the red light and the near infrared light. But similarly, we can do other types of image classification. I spoke previously of we're just looking at the colors, and I also said that the computer can look at lots of colors at the same time. It's not constrained to just looking at the R and the G and the B, 3 colors at a time like our eyes are. It can actually look at multiple colors all at once. So it doesn't necessarily need to use the NDVI, although the NDVI is a very good method. For the computer, it can actually do a form of image classification where it looks at multi-band data. So it creates a sort of space, a band space that is multidimensional and looks for clusters of pixels. What do we mean by that? So very, very basic illustration with only 2 dimensions. And I've already said that the computer can do this in many dimensions, but I can't make an illustration in, doing even 3 dimensions is tricky, but 4, 5, 6, 7, 8 dimensions, forget it. We wouldn't be able to visualize it. Our brains can't deal with it. So just to illustrate, let's reduce this back down again to 2 dimensions, and then believe me when I say that for a computer working mathematically, you can do this multi-dimensionally. You can calculate this by hand multi-dimensionally, but you can't visualize it multi-dimensionally. So let's just look at 2 bands of data, the red and the near infrared. And if we go across our image and we pick out each pixel and we look at the value in that particular pixel and say how strong is it in the red and how strong it is in the near infrared, and we plot it on a graph, say, on this plot here. So here we have the strength of the signal in the red, and here we have the strength of the signal in the near infrared. And we plot our pixel there. That position is not related in any way to its geographic position in the image. It's just purely the strength of the signal in the red and the near infrared. And as I said, we can increase this to other dimensions, so that we're plotting in the near infrared, red, green, blue, many, many different bands. And we can end up with spreading the pixels in the image going from the spatial to this band space, where they may perhaps, hopefully, cluster in certain regions. If we analyze that clustering and say, well, all the ones that sit together are one thing there, and all of these over here that sit together are another thing, and all of these over here are a third thing, and so on. That gives us a way of analyzing our image and looking at the colors. If we expand that concept broadly to include lots of different wavelengths, so that the colors are specific to particular types of objects. So we're using our spectral signature, actually using the spectral signal, the bits that we can see, to determine what the object is that was emitting this light. So let's just look at this. If we now want to try and analyze these clusters of pixels, here we have our spectra here, and here we have the bits that are visible to us, or to our sensor. So if we were to read off in the red and the near infrared a signal that was something like this, where would that appear on the image? Well, we would have a fairly low in the red and fairly high in the near infrared. That would suggest vegetation. Up here for the snow and ice, well, that's strongly reflecting in both the red and the near infrared. So we end up with a cluster here. So anything that sort of ends up here is suggestive of it being snow and ice, perhaps, or perhaps clouds. But we're going to say it's snow and ice for now. And then if we have data that looks like this, where it's weakly reflecting in both, then we're probably in water down here. And so that a cluster down here that's weakly reflecting in the red and weakly reflecting in the near infrared is probably water. So this is a pixel by pixel analysis. And so we find these clusters of pixels and say that these all belong together. As we've looked at this now, we've kind of gone the wrong way round. I mean, we looked here and said, where do they end up there? What we would do in a normal image classification is we would look for these clusters, and then we would say, well, what do they represent? Well, given that that is low in the red and low in the near infrared, it's probably going to be water down there. And then we might find this cluster and say, well, that's strongly reflecting in the near infrared and weakly reflecting in the red. Something that does that is probably going to be vegetation. A cluster up here with a strong reflectance in the red and a strong reflectance in the near infrared is going to be one of these two. Now we could separate these out more by using more bands, but as I said, can't visualize that very easily on the screen, so we'll just have to take it for granted that the computer can do this, can create this multi-band space. And more advanced methods now that are becoming more common are that we do this analysis where we make a best guess of what each pixel represents, and then we further analyze. We then go back to the spatial domain and then say, well, can we increase the performance of our analysis by saying, what do our neighbors look like? and then if they all seem to match up and come to the same conclusion, we'll define an area, an object, and we say that this object is probably then going to be this thing or that. And what sort of variation can we expect within an object? For example, trees will have areas that are dark and areas that are light because of the nature of their form and their shape. Areas that are in shadow and areas that are illuminated. So you could try looking for that. We won't be doing that sort of analysis on this course. We will just be looking at this simple pixel by pixel image classification.